So the next step in solving the linear programming first example we're going through graphically is to start graphing some what are called isoprofit lines. Okay, so again, a little refresher here. Our example is the following. We're working through an example where we have two products we're producing, and we have product A and product B. They require a different number of hours of molding and shipping and finishing and painting. Shipping, they can only ship so many of product A. They don't require hours of it, sorry. But yes, so that's the problem that we're working with. And what we're looking to do is maximize our profit related to selling both of those products. Product A, we earn $20 per item. Product B, $30. Okay. And now we have set up what's called our area of feasibility. See my previous video, the one just before this, for the area of feasibility. So here it is. It's this yellow shaded region. Next, what we're going to do is overlay the profit function graph on top of it. Okay, so our profit graph is, or to do it, what we need to do is the following. We need to make what are called isoprofit lines. So our profit function is the following: 20xa plus 30xb. Okay, and now what we're going to do is we're going to play with different values for our profit and graph those lines. So really what we have right now essentially are three variables: the profit, xa, and xb. We could not graph this graph on this two-dimensional graph. There we go. So sorry about that. We couldn't graph this guy on a two-dimensional graph right now. We would have to plot it in 3 dimensions if we wanted to actually plot out the profit. So what we can do are what are called isoprofit lines. Good. Okay. And so the isoprofit lines are where we pick a constant value for the profit and we go make our lines accordingly. Now, I have decided to go up to 150 in the XB, and actually I could go up to 150 with XA also. So to figure out a nice value for my profit, I'm going to play a little bit with these values. What if I went up to 150 for my my XA? That would put me at a maximum profit of 150 times 20, which would become 3,000. So what if I did that? Okay. Okay, so an isoprofit line I could work with is a profit of 3,000. So let's try that out and see what that looks like. So again, just play with values of the profit, pick kind of a method that makes sense to you and see what that gives for a profit line. Okay, so let's say I picked 3,000. So to plot this, again, experiment with different values for XA and XB like we did before. So I'm going to do 0 for XA and see what my XB is for starters. What that ends up giving me here, sorry for all the scrolling around, when XA is 0, XB turns out to be 100. So 0, 100 is a point on the line. When you go divide both sides by 30, you're left with an XB at 100. Good. You'll have to forgive all of the piano sounds in the background here. As you might already realize, school is closed for the rest of the year, so you're going to hear children in the rest of these videos at some points or another. Okay. Now, let's figure out one more point on this line, so I'm going to let XA be variable and put XB at 0. and again do the isoprofit line at 3,000. This puts us at an XA value, divide both sides by 20, an XA value of 150. Good. So this gives me a profit straight line that crosses through 0 and 100 and 150 and 0. So when x is 0, or when XA is 0, XB is 100. When XA is 150, XB is 0. Okay. And there we go. I'm going to connect the dots here to get my first what's called isoprofit line. Oh, sorry about that. Good. You have to bear with me here. Sometimes my pen is a little bit picky. There we go. Good. So this is our very first isoprofit line. This is the line where the profit equals to 3,000. You don't have to have these lines perfect. You just kind of play with them. The whole point isn't to pick the perfect line. The whole point is to kind of see how the profit looks. And we'll make sense of this later, but you see how it looks and kind of what angle it's on and compare it to the area of feasibility, and it'll help us see where we should, where our optimal point is. So this profit's a little bit high. Let's try a profit now of 2,000 instead. So this was our isoprofit line for 3,000. Okay, and let's try 2,000 and see what we get. Let's try 2,000. So 2,000 is 20XA plus 30XB. And now we have 2,000 equals to 20 times 0 plus 30 times XB gives us, let's see, 2,000 divided by 30 gives us 167. Can that be right? Or forgive me, 66.7. So when XA is 0, XB is 66.7. And now for our next point on the line, when XB is 0, XA is going to be 2,000 divided by 20. That gives us 100. Good. Okay, so here are 2 points on the line, and let's see here. Let's put them on our line. So this is our next isoprofit line. It's when our profit is 2,000. So we have 0 and 66.67. So here is 70. So it's right. There's 65 right around here. Sorry. That's our 66.67 or 66.6 repeating. And then 100, 0 is right here. Okay, good. And there we go. Okay, so that's our next isoprofit line. This is the line when the profit equals to 2,000. Okay. Now, the reason we make these profits, again, they don't have to be perfect, but what we can kind of see is a trend here. And you'll note that all the profit lines, or what are called the isoprofit lines, will run parallel to each other. Okay, so I'm just going to just rough out another one here. Good, like that. Okay, and you'll notice I didn't even actually go calculate what it is, but I just drew it parallel to the isoprofit line at 3,000. Notice that the isoprofit line at 2,000 is parallel to the 3,000. So you'll notice kind of a movement here, or how the profit is. So what we can do here is kind of figure out which direction the isoprofit lines are running in. Forgive me, that's a little bit squiggly. And that helps us see where our optimal solution is. Now, talking about our optimal solution, what we're actually looking for, we're looking for the most outer point on the area of feasibility we're looking for the most outer point that touches one of the profit lines first. So, okay, so if you'll notice here at this isoprofit line right here, we have a profit of 3,000. Our next isoprofit line we drew was a profit of 2,000, and so on and so forth. So as we go lower here on the graph, our profit decreases. So we want the highest profit possible, and we need to be still within the area of feasibility. Well, the optimal solution then will be somewhere at the very outer edges of the area of feasibility, and it will be where our highest profit is. So what we do is we keep graphing the profit until we touch the outer edge of the area of feasibility. So you can keep making lines here until that happens, and hopefully you can see here as I'm going, the line, the isoprofit line first touches this point right here as we drop the profit down. So again, we don't want to drop the profit down too much. Our goal is to have the maximum profit but still be within the area of feasibility. So as we drop down, 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 the very first point we hit on the area of feasibility is right there. And so graphically we have solved for our maximum point. It's right at whatever this point is. Now we can roughly look at that point. It's roughly at xb equals to 50 and xa equals to right about 20. Okay, so it's approximately at 20, 50. We can actually perfectly solve for it by looking at which lines intersect right there. So going way back to our constraint graphs from before, we can figure out which lines were touching each other and figure out what the value is of the point right there by figuring out which two constraints made up these boundaries that made up this edge of this area of feasibility. Okay, so let's go have a look here and see which two those were. Okay, so going way back here, it turns out that the finishing and molding were the two graphs that we're working with. Let's have a look here. So the molding was the green line. Okay, so here's our molding. Turns out that it is this line right here is our molding. Okay, and then it turns out the upper line, this guy, was our finishing. My graph got a little bit busy. When you're doing it yourself, it might be easier for you to tell. I'd recommend color coding. I kind of overwrote over the colors that I had before, but if I'd been a little bit more strict with my color coding, I would have seen that it would have been actually the green line and the red line right there. Let's just color code them properly. So this one would have been the green line right here. It's hard to see now, but that was the top. Well, sorry, that was the green line right there. That was the part of the molding line right in here. And this one right here was the top of the finishing straight line that we drew in the previous video. So where they intersect is going to be our optimal solution, where our profit is the highest possible while still being within the area of feasibility. So let's go figure out where our finishing and molding constraints overlap. Okay, so they occur at the intersection of the molding and the finishing. Constraints, if you will. Okay, so our molding constraint was the 3xa plus the 3xb. was less than or equal to 210. Now we're going to be right at that top of that line, so we're going to be at equals 210. Finishing was where XA plus 2XB was less than or equal to 120, but again, we're right at the edge of both of those constraints, so we're going to switch those less than or equal to symbols to strictly equal to symbols. If that makes no sense, don't worry about that, just follow the steps that I showed you before. And then once you've done your graph, let's just go back to it for a second. You see which two constraints intersect to get your optimal solution, and then just go solve those two equations that you get from those two constraints. So again, this guy was from the molding, this equation was from finishing, and we just go solve for them simultaneously. I recommend using substitution. You can use any method you want though. So first of all, I'm going to go and solve for XA in the second equation here, the finishing equation, and then I'm going to go substitute that in for XA in the first equation, and let's see what we get. So 3 times 120 minus 2XB plus 3XB equals to 210. And this gives us 360 minus 6XB plus 3XB equals to 210, which gives us negative 3XB equals to 210 minus 360. Divide both sides by negative 3. And we get that XB is going to be positive 50. And now XA, let's see what we get there. It's going to be 120 minus 2 times XB, which is 50. And this gives us 120 minus 100 gives us 20. So our optimal solution is when XB equals to 50, XA equals to 20, and that gives us a profit of the following. 20 times XA, so 20 times 20, plus 30 times XB, so 30 times 50, which gives us 400 plus 1,500 gives us $1,900. So our optimal solution is to produce 20 units of product A, 30 units of product B, giving us a maximum profit of $1,900. Okay, in the next video I'm going to talk about how to do this in Excel using Solver, and then after that we'll start talking about what's called sensitivity analysis. That's where you decide which constraint is what we call binding. We actually already know that. It's our molding and our finishing that are the two that we use all of the resource up. So we use up all of our hours in molding and all of our hours in finishing right now. And we don't use up all the other ones necessarily. But yes, sensitivity analysis will help us sensitivity analysis will help us decide what constraints are what we call binding. So those are the ones we're fully using up, and it will allow us to see what happens if we slightly change. Let's say we add more molding hours or more finishing hours. What's going to happen with our solution if we do that?